Greetings, CVM workshop attendees and coordinators. Thank you for this opportunity to present our ongoing work. I, Elizabeth Berg, am a PhD candidate at the University of Utah and will be discussing our joint inversion of Rayleigh wave phase velocity, ellipticity, and receiver functions, expanding to the shallower and deeper crust. Our work stems from previous publications in JGR Solid Earth by myself in 2018 and by Hongrek Chiu in 2019. Both of these models are also available through the IRIS EMC repository. Our newest model, shown today in preliminary results, includes shallower and deeper sensitivity through including new and expanded data. We accomplished this through the use of Rayleigh wave measurements and receiver functions. Rayleigh wave measurements include phase velocities, or the speed at which the phase of a Rayleigh wave propagates through a medium, and h/v, or horizontal to vertical ratios, which is sensitive to near station ratio of a radial to vertical particle motion. Note that h/v is sensitive to shallower structure compared to phase velocities for the same periods, as shown by the sensitivity kernels computed for a location near the San Jacinto Fault. We include surface wave measurements from both ambient noise and from earthquakes. Our 2020 results also include azimuthally average receiver functions, which are highly sensitive to near station horizontal interfaces such as the MOHO. Receiver functions resolve P to S conversions due to structural contrast from teleseisms via deconvolution. We combine these datasets using Markov chain Monte Carlo joint inversion, which enables us to quantify uncertainty and sensitivity of our model. Specifically, our datasets consist of h/v ratios computed by Kostas-Gogas, expanded now to 2 to 26 second periods. We also use phase velocities via iconal tomography from Hongrek Chiu's 2019 published model from 2.5 seconds to 16-second periods computed from ambient noise cross correlations. We use Helmholtz tomography to obtain longer period phase velocities from regional to teleseismic events. We also include receiver functions from Dr. Vera Schultz-Pelcom in our Markov chain Monte Carlo joint inversion. Here we have an example of the ZR, ZZ, RR, and RZ cross correlations bandpassed around 4 seconds period and corresponding particle motions. You can see that the receiver station h/v recorded at station WBS in the Sierra Nevada mountain foothills will be low as it is elongated vertically and not as significantly radially. In comparison, the source station, FMP, in the LA basin is elongated radially and not vertically, and so it will have a higher h/v ratio. This is sensible due to the strong contrast between soft sediment and hard bedrock in the LA basin, which leads to higher h/v ratios. Here we show h/v ratios in log time space from minus 0.15 low h/v to positive 0.15 higher h/v at 3 seconds, 6 seconds, 10 seconds, 16 seconds, and 24-second periods. We can see higher h/vs in the Ventura, Central Valley, and LA basins, as well as in the Salton Trough. We see lower h/v ratios in the Sierra Nevada mountains and in the Peninsula ranges. With increasing period, we also see lower h/v ratios in the basins as our sensitivity moves to below the soft sediment to hard bedrock basin interface. Here we show phase velocities published in Chiu et al. 2019 at 3.5 seconds, 6 seconds, 10 seconds, and 15-second periods. We see low phase velocities in the Central Valley, Ventura, and LA basins, as well as in the Salton Trough. We see higher phase velocities in the Sierra Nevada and Peninsula ranges. Note that limited resolution at longer periods is determined here via station configuration criteria due to fewer stable measurements from ambient noise cross correlations. See Chiu et al. 2019 for details and final model. In order to obtain longer period phase velocities, we use Rayleigh waves from magnitude 3 and larger regional events up to magnitude 6 and greater teleseismic events. Overall, we look at over 700 events from 2015 in order to resolve longer period phase velocities. Helmholtz tomography is similar to iconal tomography in that the slowness, or inverse of phase velocity, is related to the spatial travel time gradient. However, these longer periods also require a Laplacian amplitude term in order to properly determine phase velocities. Here we show the record section of the ZZ component bandpassed around 18-second period centered around the Rayleigh wave arrival from a regional magnitude 4.43 event. We show the seismograms, FTAM picks for the phase velocity at this period after 2-pi jump correction, and corresponding amplitude measurements. Here we show a similar record section, but for a magnitude 6.3 teleseismic event that passed around 30 seconds. We use this event to now show you our data, including the phase travel time computed at each station and interpolated onto the grid. Similarly, the amplitude at each station and interpolated onto the underlying grid, and the spatial gradient to give iconal tomography or apparent phase velocity, and the amplitude Laplacian term shown here. We combine these terms together to resolve our Helmholtz equation and obtain our phase velocity, corrected phase velocity map for this event. We repeat this for all events where we have strong signal and combine them together to obtain our mean phase velocity map. Here are phase velocity maps from Helmholtz tomography for 15 seconds, 24 seconds, 30 seconds, and 50-second periods. We see lower velocities beneath the Central Valley and then beneath the Sierra Nevada ranges at longer periods. We see lower velocities beneath the Central Valley and then beneath the Sierra Nevada ranges at longer periods. We see lower phase velocities in the Salton Trough and faster phase velocities in the peninsula ranges. We compare iconal phase velocity results determined from ambient noise by Hongray Chiu et al. In 2019 to the newly obtained Helmholtz phase velocity results from regional earthquakes to teleseismic earthquakes, mainly regional earthquakes at this period, and see similarities in the peninsula ranges, LA Basin, Central Valley area, Eastern California shear zone, and at the San Andreas, San Jacinto fault junction. We note differences in these results stem from the difference in resolution between the northwest and the southeast corners. We also compare a long period result to those reported in Yang and Forsyth in 2006. We see consistently lower phase velocities beneath the Sierra Nevadas and higher phase velocities beneath the peninsula ranges. There are lots of similarities between these maps, but we will not dwell on this for long due to the very large difference in resolution between these results. Here we have an example of our Markov chain Monte Carlo results. Our MCMC inversion is based off of our 2018 and 2020 papers, so please see that for details, although we will cover that in brief here. We have a two-step in our MCMC inversion with higher weighting of the receiver functions in step 1 and a larger model space. Here we are showing shear velocity versus depth from 0 to 10 kilometers and depth from 0 to 100 kilometers. Our model space area in general is shown in the green dashes. Our starting model is based off of our 2018 results and the Lee 2014 model for the MOHO and upper mantle. When we forward model the red here, which corresponds to our starting model, we obtain the receiver function shown in red here with time of the receiver function versus receiver function amplitude, phase velocity in period versus receiver versus phase velocity, where the red starting model corresponds to the red triangles here, and H over V for period versus H over V ratios as red triangles here. Our data is shown here in black with the weighted uncertainties. Our weighted uncertainties for the part 1 has higher weighting for the receiver function, and so our uncertainties for phase velocity and H over V are much higher, versus in step 2, we use our minimum misfit model from step 1 and relatively weight all data sets equally in order to get our average model of the posterior here, shown in white. All posterior models, which relatively well fit the data, are shown in light blue for both the shear velocity model space and for the receiver function, phase velocity, and H over V ratios. Here, this is a station at the foothills of the Sierra Nevada range, which we have looked at previously. And in general, we see faster phase velocities near the surface. And similarly, this is just another example with kind of a wonky receiver function, but highlighting that we are able to fit our relative data sets. And this station is in the peninsular ranges. And we also see faster velocities in the mountains here, which is what we would expect. This is an example of a station in the Salton Trough. with thicker sediments. Reverberations of body waves in the soft sediment layer results in this delayed first arrival within the receiver function that has been tricky to fit and causes an interesting overall receiver function. This station we are able to fit, but we are still working on model parameterization needed to fit all basin stations. So at this time, we have a relatively limited scope. We now compare our MCMC results thus far at each station, interpolated onto the whole map. Note that these results are preliminary, and we are working to include more stations. Once we have stable results from the inversion at each station, we will perform a follow-up joint inversion with our h/v and phase velocity results at each grid point using this interpolated map as a starting model. Major differences between our preliminary 2020 results and those from 2018 stem from lack of stations in a specific region. This will be fixed in our follow-up grid point inversion to resolve structure between stations, as well as by including more stations with receiver functions. We see similarities in low velocities in the Salton Trough, Central Valley, and Ventura basins. We also see higher velocities in the Peninsular and Sierra Nevada ranges. We also compare our deeper results and see some of similarities and differences. Main observations are lower velocities in the Eastern California shear zone, fast to slow velocities in the Sierra Nevadas, which is consistent with previous results and with more recent US array models as well. We also compare our MOHO depths to those from our starting model based on the Lee 2014 model. We see similarly deeper MOHO in the Sierra Nevadas and Peninsula ranges. And we see shallower MOHO in the Salton Trough and in the coastal ranges. We also consider depths of 3.1 kilometers per second, or relatively faster than expected shear velocities for sediments at depth. We see that the Salton Trough is much deeper, while marine sediments in the coastal ranges are relatively shallower. Note that this is limited due to our not including basin stations yet, and so we are looking forward to obtaining stronger results in this area going forward. We now review our misfit to our data sets. Our current inversion scheme results in higher misfit from surface wave data, mainly contributed from h/v compared to good fits of the receiver function, as that is our focus at this time. However, many basin stations are currently not included due to difficulty fitting the initial early arrival in the receiver function. We are working to alter our model parameterization in order to fit all of our data. Thank you for your time and attention, and please visit our SCEC poster for updated results in a couple of weeks. Thank you.